Okay, welcome back to our course on smart energy distribution. Last time we have looked at self-organized balancing power. There were several topics that we addressed there. I had shown you something about the logical structure of the power grid. We had looked at the situation of how to actually manage a balancing group, the different situations that we have there, whether the balancing zone has a surplus or deficit, the different ways of actually knowing whether you will get money for having a surplus or have to pay for that. I showed you something about customer response. Yes, then I showed you something about a way of establishing some kind of cascaded, self-organized balancing power in a very decentralized setting. We looked at this situation where we have many devices in some region which are connected into a pool, and the idea is to, starting from some stable schedule, if there are deviations, how one could actually even out those or balance out those deviations from equality between demand and supply. And we showed that different ways of doing that, like using devices which can generate additional power or reduce the generation of power, or using prices which lead to different responses. If the price incentive is too large, you get avalanche effects which you cannot control really. So just to use prices is not a reasonable idea, although you see that in many places that people say they would like to use prices, but you cannot control it, what happens. And then we looked at ways of actually controlling what's happening, and there we had this idea of using the pool of devices which have certain devices which can be controlled, which can offer some flexibility by modifying the intervals at which they actually need power. Here, like a fridge, is an example of a device which can offer flexibility without needing the interaction with users, because you just have to comply with the temperature range, and if you do that, everything is fine. We looked then at ways how actually one would be able to use such a pool of devices to organize that certain devices have their demand at a time where another device wants to offer something. We looked at the way or how one could specify the flexibility that devices have, and we looked at optimization problems. I showed you that like how one typical approach to optimization, in particular evolutionary algorithms, work. We looked at the different ideas about that, showed you ways how the individual, the sequences or the sequential steps in such a evolutionary algorithm with selection, recombination, mutation, and then environmental selection to get the next population. I showed you something about the representation, about selection mechanisms, where the best is the tournament selection. I showed you something about recombination and mutation, and we looked at survival schemes like the environmental selection to determine which element actually gets to the next generation. And so there are several, like 4 different methods that I showed you, where the number 3 and 4 usually are used in connection with evolution strategies. That's where they have been designed, and it's always a way of like how you can actually determine the selection pressure and make sure that you don't lose potentially well-performing solutions. I showed you briefly this slide where I made remarks on complexity. I very briefly told you what an NP-hard problem is, what an NP-complete problem is, and how we can argue about that. And these are problems which look to be quite difficult, so we usually use some heuristics or meta-heuristics, or at least know that it will take some time to get a really optimal solution. Okay, then we looked back again into our optimization problem, looked at local search approaches, looked at again at the device pool, how it can be used for that, for optimizing the balanced schedule again. And there was this simulation model, and then we had the final idea of the elite group. And I showed you that this is an idea where we have this cascaded version, where we have an immediate response from the elements in the elite group, and then a little bit time delayed response if necessary from the pool. And in this way have something which resembles in some way the balancing scheme that we know from like primary, secondary, tertiary control. Okay, so that was that chapter, and yeah, that was more or less it. I showed you some results of that scheme for balancing power. And then we went already to the next chapter, which is chapter 4 on smart homes. And here we somehow this is yeah, okay, so this here we looked at initial things. I showed you again something about our projects that we had. This was very brief. I'd shown you that before. We looked at flexibility potentials, looked at the integration of electric mobility, and this is the first slide for today, which is new. So we had come to this project where the idea is to integrate electric vehicles. It's obvious that electric vehicles need electricity to transform that into mobility, and somewhere they have to get that, so they have and they have to store it, so they have batteries. And in order to make statements about the potential effects of electric vehicles with respect to the energy system, we certainly have to look at several characteristic properties. And one property certainly is at what times they actually will be available for being connected to the system. And what we see here is that if you look at the typical mobility of people, then like here it's stated for the year 2008, but this does not change very much. So it shows that the average daily car usage of typical privately owned car is less than 1 hour. It means that more than 23 hours this car is parked somewhere, and either at home, in a garage, or somewhere in a larger parking garage, or or on a parking lot of the company where the owner is working, or at a supermarket store, or at a stadium, wherever you have to leave it. But usually we don't drive that much, and like 94% of the trips are less than 50 kilometers. Now people always complain that electric vehicles are useless because they don't offer the range that is needed, but this shows that for typical mobility patterns it would be easily sufficient. And that's also known from daily experience that certainly we go over longer distance now and then, but not every day. And just for the typical day-to-day mobility, the distance that we travel is not that large. And now, if we look at the capacity of typical EVs nowadays, like 20 kilowatt hours is something which is more or less standard. Meanwhile, for electric vehicles, we know that there are others. For example, the Tesla usually has 65 to 85 kilowatt hours capacity, which has an interesting effect, by the way. So, like we know that with 20 kilowatt hours, you get you can have a range of around 100 kilometers. And if you have 65 to 85, you have something in the range of 400 kilometers range. And it shows that if you want to travel over a longer distance, and you certainly, like over time, you travel a longer distance to cover a distance of, let's say, 1,000 kilometers, you have to recharge your battery 10 times if you have a 10 kilowatt hours battery. And you only have to do that twice if you have, or twice or maybe 3 times if you have a very large battery. And it means the number of cycles that you have to use on your battery is much smaller if you have a smaller battery. If you have a larger battery, a battery with much higher capacity. And it means that since the number of cycles that you need to travel over a certain distance is much smaller, you can actually afford to have a battery which is not offering you the same number of cycles as this battery has to offer, this smaller battery. And so you can use lower quality products, and that's exactly what Tesla is doing. They use lower quality products for their batteries because they give guarantees over 10 years because the number of cycles that they have to guarantee for is much smaller than the number of cycles than the competitors have to guarantee if they provide just these small batteries. Yeah, certainly the problem is that a large battery is much more expensive than a smaller battery, but so the car is much more expensive. So the Tesla is in the range of rather 70 to 90,000 euros, whereas the other cars are in the range of something around 30 to 40,000 euros, but they offer 3 times the capacity. So Tesla is doing a good job in actually offering electric mobility. But this is just a side remark. But the major point here is that I wanted to mention is that having a larger battery means that you need fewer cycles, and it means that your battery will live longer because the battery ages with a number of cycles to some extent. And so since you only have a limited number of cycles that is guaranteed before the capacity is going down by more than 20%, that's normally the limit that you would tolerate, then it's just a better approach to have larger batteries. Nevertheless, let's just consider this calculation here. Assume all our vehicles, electric vehicles, that are expected or at least hoped for the year 2020. Yeah, just a simple computation. If we assume to have 1 million battery electric vehicles with 20 kilowatt hours capacity, that would mean that we have a storage capacity of 20 gigawatt hours. Yeah, so 20 gigawatt hours, normally we have, if you look at our demand or the typical demand during the day, is that we have something around or between 50 and 70 gigawatt power demand in the peak. So 20 gigawatt hours would mean we could provide about as much as we have, or that's about the power that would be provided, for example, by solar panels on a good day for 1 hour. Now, this computation is not sound because to provide 20 gigawatt for 1 hour, you would need a very high capacity. You would need 20 kilowatt connection. Now, usually we assume that if we have like one phase connection to the electricity system, and if we can charge at 16 ampere, that's around 3.7 kilowatt, it would mean that we could offer 3.7 gigawatt of power if all the 1 million vehicles would be connected. 3.7 gigawatt is about 3 nuclear power plants. Yeah, just to see what that actually means. Now, this is the global view. If all the vehicles would be connected, and we know they would be connected in the low voltage grid, we know that can pose some problems to provide power for the upper levels, but at least we could provide some power from the electric vehicles. But it also means that we have to reach out. Like I just said, we could provide power, 3.7 gigawatt. but we want to recharge the batteries, we have to provide that much additional power if we have 1 million battery electric vehicles. And that means we would need about 3 nuclear power plants in addition just to recharge the batteries. And like in total, I told you, or if you look at the average range of a vehicle, like or the distance you travel over a year, something, if you assume you have 15,000 kilometers over a year, you would have something like 3,000 kilowatt hours usage of electricity. That's about the typical annual consumption of a household. Yeah, so that would be, if you have 15,000 kilometers distance that we drive, travel distance over a year, that's about the same as the energy consumption of a typical household. Just to see how much that is. So, my point actually will come after this that I want to make. So, we have a high demand for power, potentially also a high supply of power if we can have power feedback, which so far the car manufacturers don't want to provide, which in Japan is mandatory, that they have to be able to provide power from the cars, because there they have, as you know, closed down most of the nuclear power plants, and so they have again and again shortages of power. And so they had situations where electric vehicles were used to power or to provide the power for traffic lights, for example. Yeah, so they actually are needed there for emergency power supply. Now, the interesting point is the average time for charging. How long is that? They want to be recharged. If the battery is completely empty, 20 kilowatt hours would need, and you have single-phase charging, simple charging, 5 to 7 hours. Now, if you allow a little bit more, if you allow 3-phase charging, then you have something like 11 kilowatt, would mean around 2 hours. If you would agree to have just 80% state of charge, it would go even faster. Now, this has to be compared with the average daily car usage of less than 1 hour. That means you have a few hours per day where the battery has to be recharged. Like we drive only 50 kilometers, so it's only 10 kilowatt hours that you actually have to recharge if you would drive exactly 50 kilometers. So the amount of power you need every day is not that much, and you don't need much time to recharge the battery, to refill the power or the energy that you have used for being mobile. And since the cars are parked most of the time, there's a long time where you can actually put those 2 hours or 5 to 7 hours. So we have a very long time period from being parked, like starting time, finishing time. And then you have here, at some point in time, you have here your charging demand. You can move it somewhere. Move it somewhere without actually influencing the vehicle in some negative or unwanted way means that there is a high potential for flexibility. You can shift the load for recharging the battery quite freely over a long period of time, assuming that a car, for example, is at home in a garage. There you have a lot of time. If you are sitting, or if you are having parked your car on the curbside, and want to get power from a public charging station, then there might be others who also would like to get power, and then you would be expected to leave the charging station again as soon as you have reloaded your battery. But 85% of the electric charging stations are assumed to be in private ownership, be at home somewhere, and so most of the time the cars will be sitting there, and there's a long time for actually providing the electricity. And so we have this high flexibility for load shifting, and you know that that's what we were looking for. We wanted to have devices which can be used in a very flexible way. And here they are. There's an extra need for electricity, but we can shift the load. Certainly there's the potential of high peak load, and I will show you on the next slide what that would mean. And obviously, if we control the charging of electric vehicles in an intelligent way, we can actually try to stabilize the grid or follow the supply curves. You have a question? Yes. Yes. Maybe. And then you will tell the system that you would like to, like the question was these are just average figures. And so on the specific individual case, it may be that you want to have charging as fast as possible. Yeah. And then you would do that. But so the requirement is similar to getting flexibility from a washing machine or something like that. The user has to specify at which time he actually needs the vehicle again. And now there's an incentive to specify that. So if the user should say, okay, that's the starting time where I park the car and I need it 5 hours later or 2 hours later or whatever. And I only want to have the battery recharged completely immediately before I'm leaving. Because that is something which has to be or looked at. If a battery is fully charged, and if it's standing around being fully charged, it's aging. It's aging much more as if it would be just charged to 70% or something. So it is in the interest of the driver to state at which point in time you would like to leave again, because then you know that you have to provide full charge. You can actually prepare the car for being able to leave by, for example, preheating it with electricity from the grid, or cool it down, or whatever you have to do there. And if you have that information, you know this is my degree of freedom for actually providing the power to the car. On one day, it may be just almost no degree of freedom, has to be charged as fast as possible, but in many occasions, it will be possible to do that over a longer period of time. Yeah? This has to be specified, definitely. It needs user interaction. And it may also be that you would like to have a certain minimum level of charge, so that you have a minimum distance such that you can just come back at any time, and you are sure to have a minimum range that is guaranteed. Yeah? So these are things that all have to be considered. Okay. Now what do I mean by using the charging needs to balancing, or for balancing purposes? So if we assume that, like this shows in black, the power consumption of one segment of the low voltage grid, like around 100 people, 100 houses, over one day. And now we have electric vehicles which are coming in addition to that. And if we assume most of them are returning to their homes in the late afternoon, then we will have this extra charging needs here, or extra need for power in the evening hours, where anyway you have the peak demand already. So this would be very unfavorable to do it like that. So there would be several ideas how you could use flexibility. You could try to move all that demand here to some night hours where you have situation which is okay. You have low prices. You have not that much load anyway. So that could be favorable. You could say, I would like to have renewable energy only. And if your car is parked or is connected to the grid at this time here I indicate power generation from the sun, from solar panels, then you could recharge the battery. And you could even, if you can recharge, or if you can feed in power into the house again, you could actually even out those load peaks in the evening, if the car can do that. And then you would be able to generate a load curve which is visible to the grid, which is the green curve here, a very flat curve, if that is something which is favorable for the grid. Or in general, you could say that the flexibility of battery charging could be used to actually construct or generate just the demand profile that is beneficial for this day. Maybe next day in a different way, but you could generate a range of different demand profiles. That's the flexibility that would be offered and that we should be able to exploit. So that's why we are interested, certainly we're interested in integrating the electric vehicles because we have to provide the power. But since we notice there is a high potential for flexibility, this should be used. Okay. And this was actually the reason why we were able to build that smart home, the Energy Smart Home Living Lab at KIT, on KIT campus, which we should be able to visit that. Maybe next time we could go there and just have a look what kind of technology is in there. So it doesn't look like a smart home, but it is smart from the inside. It doesn't look very nice, but you see there are panels on the rooftop and some other things. From the inside, it looks quite nice. There's a vehicle outside, or used to be there, and I will show you more about the ingredients of that house a little bit later. So we talk about a smart home, because we want to integrate the electricity needs of the vehicles into the home or into the grid in an intelligent way, so the best would be to have a smart home interface for that. Now, the meaning of it, or the notion of a smart home has been around for quite some time already. So just if you look at literature on smart home, you find a lot of, or many publications about that. And so normally smart home has to do with home automation. So remote switches, you would like to control your lights, your windows, maybe your coffee machine, you can open or close the door and things like that. You have home security and safety, smoke detection, a very important thing, dog communication. Ambient assisted living is an important part, in particular support for elderly and disabled people. Have some extra devices or observe how lively some person actually is. If you are in the care business, care for elderly people, you would like to know if there is a need to actually look after these elderly people or whether everything is fine. So this is something which is a relevant scenario. Also multimedia home, there are displays where you can actually control the music. You have email access, you have all kinds of communication interfaces meanwhile that are offered just by some displays in your house. So this is the typical smart home interface. Now we add energy to that. Energy did not used to be included in these scenarios. Actually, the energy consumption of the typical smart home or home automation systems is quite high, because the rationale behind that was, well, they look at or home automation is something which is mainly in commercial buildings, not in private buildings, and their energy consumption is not that much of an issue. That was the rationale behind that. So now we look at energy consumption, and so many things change there. And in particular, we look at the ways how we can actually control the energy consumption with technologies that we know from smart home. We have to communicate inside the house and things like that. So this is what we focus at in our KIT smart home, and also in other scenarios. We don't consider that much comfort, security, and health. So the energy scenarios have to do with having smart metering systems. So know something about how much energy is actually used in the house. Then also we would like to control energy consuming devices, so energy management is important. And we have some extra signals like prices for electricity, power limits and things like that. Then there are interdependencies between households and the distribution grid. Certainly, if you have too much demand in your household, you might get problems. We would like to integrate decentralized power generation, from the rooftop and maybe from micro-combined heat and power plants. We have smart domestic appliances, at least would like to make them smart by being able to in some way get information about their current status and control them, control the time at which they are running, control a fridge, I mentioned that before, or a deep freezer or a fridge, heat pump, air conditioning. These are interesting devices. In particular, these here, the second bullet points, they are important because there you only need temperature corridors to control them, whereas for the washing machine you need interaction with humans because you cannot start a washing machine, or it doesn't make sense to start a washing machine without having it filled with laundry before. And then we want to integrate electric mobility concepts, and the optimization goals here are quite different. Can be to minimize energy consumption. This would be one of the traditional goals. So people, if they are confronted with these technologies, very often they just ask, and how much do I save? And the problem is, if we talk about using flexibility, we have to say, you don't save anything, but you're more flexible. And then they will say, so what? What do I need? What is my benefit on being flexible? And then we say, well, it's not your benefit, but it's the benefit of the grid. This is something which is hard to really use as arguments for having people to actually take part in this nice game of providing flexibility. Now this immediately shows that if you just shift load around, you'd never save anything unless you get some additional monetary incentives, but this is something which we don't have in the moment to a degree that is really attractive. So there would be ways of saying, okay, if your neighbor tells you that he's not providing flexibility with his household appliances, you could just say, what? You are using your washing machine at any time, even if there is no power available, not that much power? Why don't you wait for the time where there's more sun? Because then it's much more convenient to use it. If we have a situation or a culture like that it is normal to adjust the time of power consumption to times where we know there is more power, then it would be easier to use flexibility. Okay, but so this is one goal, minimize energy consumption would also be an effect which would be nice. Certainly minimize carbon dioxide emissions, it means have more power generation from renewables, and so again here something where you can actually save money, save money is maximize self-consumption. That means you just use yourself the power that you generate on your rooftop. You don't put it into the grid, and then you don't have to pay 28 cents per kilowatt hour if you get it from the grid. Okay, now you see all kinds of displays or icons. So what do you see here? You see the Stromampel, the energy light, or energy traffic light, you could say, from EnBW, which I have explained to you before. This here is something similar in a different version of that, where you only see indicated here with the color of those. Like in red, you have a high price. In yellow, here you have a medium price. In green, you have a low price. It's not as impressive as here, where you have the complete display is colored in the current price range and can be colored also in red or in green. Okay, different types of devices are currently being developed and getting on the market. Now, what did we do in that Energy Smart Home Lab on KIT campus? We have put in there several devices, all kinds of intelligent appliances, all from Miele, because Miele has a standardized interface called Miele at Home, actually designed for ambient assisted living for elderly people, not for them to use it, but for the people who take care of them to control the devices. But we could use them to get information on their current status and send them some control signals. So we have these appliances, we have a combined heat and power plant, we have air conditioning, we have solar inverter because there are solar panels on the rooftop, there's a smart metering system, there's a charging station outside so we can charge electric vehicles, and then there is an electric heater. This electric heater is of interest because we can use that to transform power into heat and not just gas into heat, what we do in this combined heat and power plant. So this is a bivalent way of producing heat. And then we have all kinds of displays where we provide information on the current energy situation in the house. And we also offer possibilities to specify the preferences of the user with respect to the usage of the devices. So this is the energy management panel, and all the information that is available there from the smart meter, from all kinds of sensors in the house, is collected into the energy management system. And so this energy management system is observing and controlling everything which is happening in the house with respect to energy issues. Electrical and thermal power is controlled there. And then it is a lab. So we don't want to wait all the time for the sun to shine in order to find out how we can respond to photovoltaic power generation from the rooftop, but we have a device there which is actually able to replay the generation of power physically again into the house. And then we can replay it, we can actually scale it up to higher to higher power levels, and in this way we can run experiments how we could respond to more power generation from the rooftop. And then we have a 4-quadrant amplifier, which is a control element which controls the quality of the power that we get in the house. We are connected there to the medium voltage grid, have a very stable and very high quality power signal, but there we can generate different power signals, we can make it bad, we can have phase shifts, we can have some extra frequencies on top of that, some other harmonics, and then we can see how the house actually can be controlled to respond to a bad situation in the grid and to improve maybe the current situation. So how could we respond to a bad situation in the grid, as for example possible on some island or somewhere in the desert, or at least in a remote situation where you have a stable or not so stable grid, as in India, for example, in some locations. And then another thing we have there, it's a battery simulator. We also want to be able to store electricity in the house. This is also possible. And we have there electronics in there such that we can simulate the characteristic profiles of other battery types, and then can simulate the use of batteries inside that house. So we can store power from the rooftop in the battery and use it at later times. So you see it's quite a flexible lab, and it's also possible to live in there. As you will see in a moment, there will be larger pictures of the inside, of the interior. So we have here all these devices, as I said, household appliances. We have certainly also personal computers or smartphones to control what's happening in there. We have touch screens inside the house. We have decentralized power plants. We have the photovoltaic panels and combined heat and power plant. We have a DSL router which can actually get information from the outside. And there is an electric vehicle which needs information. And we have the car driver We have the personal charging station. So all the elements are there that one needs. And what we can test there is the interplay between devices, the house, and humans. So we have these intelligent appliances, we have electric vehicles, which can be used in a bidirectional way, not just driving forward and backwards, but also providing energy from the house to the vehicle and backwards into the house. We have the power generation. We have phase change materials. Phase change materials are small packets of some kind of salt, some minerals, which melt at around 23, 24 degrees. And when they are melting, like they are put in the ceiling of this apartment there, or that house. And if it gets warmer than 24 degrees in that room, then they are melting, or this salt is melting, and then this melting consumes energy, which is a cooling effect, and so the room is cooled down just because there is this salt in the ceiling. And you certainly have to cool it down now and then, and for that you need water pipes that actually cool those elements down. So that's phase change material. This is a passive air conditioning effect. You don't need a vent to actually, or you don't need to actually cool down the air explicitly, actively, but you do that passively. I mentioned the four-quadrant amplifier, and so what we are studying there is the interaction between people living there and the technical environment. And what we certainly would like to find out is how we can actually discover and exploit degrees of freedom for energy control. Electric vehicles are sitting outside, so it was the framework was that we had this project on electric mobility, so we actually had this nice vehicle, an Opel Meriva Meregio, which was actually able to refeed or to feed back power into the grid. Daimler never managed to do that. They promised it, but never provided it. Opel cooperated with us very openly and actively, and that worked fine. And we had, in the project, we had several smarts which could also recharge the batteries there. So what we wanted to have there to test is demand-side load management, reschedule the appliances on external 24-hour signals. Now we don't have external 24-hour signals like time-varying tariffs, but we certainly could generate those time-varying tariffs or time-varying prices locally based on current market developments, which actually was done in the house. So the signal was generated locally, but in principle that could have come from the outside. And we also assumed some power limits where a typical or a simple power limit would be not to go beyond the power that is generated locally. We had to manage the load and feedback process of the electric vehicle, and the challenge certainly is to cope with the increasing imbalance of generator and consumer load in the grid, which is just there because of the renewable energy or power from renewable energy sources, and also the presence of electric vehicles, because all of a sudden we have high very high load requirements. So for example, if you look at the demands of didn't mention that before when I talked about electric vehicles, but if you look at the Renault Zoe, for example, you can only recharge it at least 11 kilowatt power. And if you have this normal or typical home, you don't have just a plug offering 11 kilowatt. Yeah, you have to ask the power or the utility, the Stadtwerke, to provide you or to offer you or to allow you to actually install special equipment providing that. So this is something which is extra load, and we have to cope with that. Okay. Now, how can we do that? We have to do that in a systematic way. And it means we look at the different devices and to try to find out their potential capability to provide flexibility. So we talk about a degree of freedom. I did that several times already. And that's the capability of rescheduling the appliance's work items. So for a fridge to reschedule this time period where it's cooling down the interior. And there are appliances having a very poor degree of freedom, where rescheduling is not possible really. Typical example would be a stove. The stove is switched on when you want to cook something, and you cannot really control it externally. If you have a deep freezer or electric heating, like a heat pump or things like that, that can be moved bidirectionally on the timeline. So if you look at that, if you want to use power to actually use your heat pump, you can move that back and forth, start a little bit earlier or later, and it is not that much conflicting with the temperature requirements. Backward on the timeline, a hot water boiler, for example, you have to provide power, hot water at a specific time. And whether you do that immediately before or 2 hours before, if you have a well-insulated hot water tank, then it doesn't matter. You have that possibility. Forward on the timeline means just this direction is something which may be available for washing machines or dishwashers if they are loaded, and the user says, okay, now it can be started, then it's good to have maybe some time interval that is given to you for running or letting the washing machine wash or the dishwasher wash the dishes, but you can move it to some later time. And now another classification is to distinguish them into controllable devices and devices which are just observable. I mentioned the stove before. The stove certainly is observable. You can observe at which time it is running, and then you can learn at which time you would normally use the stove. And then you have devices which are controllable, like a dryer or a washing machine or dishwasher, or like this is timed service. And then you have permanent service, like deep freezer, heat pump, or whatever you would like to have as devices which can or which are providing their service in a continuous way or in some intervals, and you can modify the intervals. But those which are observable then also are distinguished into predictable elements and unpredictable. So, for example, lighting or multimedia usage or small appliances are not that predictable, although you could say, okay, in the evening I will need some light. If people tend to be at home, they will have the lights on. So to some extent you can also predict something there, and it means you can predict a certain load profile that will be there anyway. And then you have this time signal or time variant price signal, here indicated in blue. There's 5 levels in this case, and this is what we had in the Meregio scenario, the model region. Different times or different prices at different times of the day, quite often called a time of use tariff, because you know beforehand, 12 hours before or 24 hours before, you know the price levels for the next day, and then you can plan to use your devices depending on the prices, and the prices are adjusted depending on the day ahead market prices that had come out from the daily auctions. And this tariff can be communicated by the energy provider, and so you have an incentive to consume power at the lowest rated periods, so just consume power at those times. No, that doesn't work, but maybe rather after 2 o'clock and not between 10 and 12 or 11 and 2 o'clock or something like that. Yes? Well, that's not realistic. These negative prices are something, certainly you could think about that, but this is something on the market for very spontaneous responses on the intraday market. I don't think that they would actually, like, certainly not as time of use tariff, maybe as a real-time price. If you have spontaneous price information, maybe that there it would be reasonable to provide sometimes also negative prices. We talked about the case that we had something like minus 10 cents per kilowatt hours. Or it was actually up to minus 13 cents. So that would be of interest. But experience tells that if you look at manual user response, it's not that important how large the spread is here, how much the difference is between high price and lowest price. The main point is it a red price or a green price? You don't want to think about that. You don't want to calculate how much is it worth today to go to that price or to that price, or can I pay for that, or should I go to that time? This does not work. You just need some relative information, and that doesn't make any difference whether you have, like for your response, whether you have 50 cents difference or just 5 cents difference. For the outcome in the end, if you say I would like to make money by or save money by using my devices only in the low price time intervals, for that certainly it is then in the end important. But this is another issue. But just to get people to be more flexible, colors can be much more of interest, or can be more effective incentives than showing you a price or telling here it's 40 cents and there it's only 10 cents. Yeah, so negative prices might be something, and certainly for somebody who's doing that in a commercial way, that's very important to know there's a negative price, then you use your power. So for the industry, that is very, very interesting. But for a home, I don't know. And we actually, like for something like this here, such a time-varying tariff, we made some simulations, some like more than 10 years ago, about the monetary effects of something like that. And we noticed that considering the typical potential of load flexibility in a typical household, we looked at an area of having around 1,000 households, and we noticed that what you can save, even on such a large spread here, is just 10, 20 euros, something like that, not more. That's even much, yeah, only if you're quite flexible. Because the spread here is not that large, and it does not pay that much, and you have certain times at which you just will consume power, and the amount of power you can actually move into those times at which it is cheaper is not that large. Yeah, so there is an effect, but the monetary effect is not that significant. This is one of the major problems in these scenarios. Okay, nevertheless, there should be an incentive to consume energy during lowest rated periods. And now let's look at an example of such a schedule. So here I have a typical schedule, which actually one of my students, that was in 2007 he did that. He just invented this typical schedule, and we're still using it as an example. So we assume that you have you have the typical profile of a deep freezer running again and again. You have a bread maker, bread machine, which should provide the new bread in the morning. You might have a toaster. You have a stove at noon. You have a dishwasher, typical dishwasher profile. Then again, you have a toaster somewhere. You have a stove usage in the evening. It may be again a dishwasher. It must be a large family having dishwasher run twice a day. And a washing machine is also running. So typical profiles that you can see. And now the question is, what can you do with that? So this is something that you have observed over the days, and you can predict that. This will be the schedule for a typical day. And now in yellow you have the price curve. And so you would like to reschedule the appliances using the 24-hour or this time of use tariff, and you would to reschedule the devices inside the degree of freedom, and then you can try to get a better situation. And for that you use these external signals, you use long-term signals like price, power limitation signals and their combination. You have short-term signals, there's current is in oversupply or undersupply, you have power factors, you have higher voltage, lower voltage, maybe you have to respond to that. You can do that also. And you would like to adapt to the to the values that you actually that are better for the system, so stabilize the voltage and things like that. And you will respond to these parameters in the energy management. And now we come now to this schedule again. On the top you see the original schedule, and now we want to optimize that with respect to this price signal. Now how could you do that? You could say that the bread maker, the bread machine, should start earlier because here is already a higher price. So you shift that backwards in time. Then after lunch, the dishwasher is postponed to a time where the price actually is low. And then you have again dishwasher and washing machine also should be postponed to some later time in the evening. So this is something which would be beneficial. So you could send out those recommendations or control the devices directly. Then there are other devices like the stove, which cannot be moved. But if you have an electric vehicle sitting outside, you could reduce the power peak, the load peak, by just getting or using the battery from the vehicle. And this is exactly the scenario that we then later on actually built in that house. Yes.
Couldn't we just extend the pool model that we saw for the...
Yes, definitely. You can extend the pool model, and then you can balance out things here, and that would be one possibility. But this is independent of the pool model. This is now just inside a house. The pool model with the elite group and so on, this was something which was a regional model, and you can combine both things. Okay, then you can, if you have used the battery, you can recharge the battery at night. Okay, so this is just to give you an idea of what we wanted to get there. This is a view of the interior space, which we will also look at when we visit that house. So it's a nice living space, and actually we had people living there for some time. And we will have them again, have some people again living there. And now what kind of information do we provide? It said there is an energy management panel. What is that for? What are the tasks? One important point is you have to inform about the current situation, the energy situation in the house. So provide information about the energy consumption. The current energy consumption, consumption history, what did you use in the past? And then you would like to discover and specify degrees of freedom for energy consumption. Both scenarios have to be supported. What we actually built there is a web application. That means this can be used on any device that can display web content. So you can use it on your smartphone. You can use it on the displays that are put on the walls there. And now how do they look like? Now let me, I hope it works. Let me, oops, here I want to, aha. I have to identify myself again. Something, I don't know why it asks for it twice. Oops. There it is, and I will have to do that again. And there you see now live data from the house. Yeah, this is the energy management panel, so we can look at it now. So this is, as you see here, up to date. This is data from today. And we see that currently there is not very much power generation from the rooftop. It's a cloudy day, just 366 watt from the rooftop. I can click on it, and we see that currently there's also very little power generation in the house, very little power consumption in the house. So you see that the border here is green, and you see also that we are actually moving power into the grid. If the power would be, the power flow would be from the grid into the house, it would be a red frame around it. And so we can now click on this here, and you see the history of the power generation from the rooftop. So you see that we had quite a bit there. Actually, it's a very bad place. It's shaded, and so there's a tree standing in front of it. So it's not the optimal way of getting power there. But you can see what the power generation in recent days was. And here we can actually, if we go on, oops, that should be some, there it is. We can look at all the devices in the house. We can specify, or I could say, okay, here I can say I would like to see what happened this week so far. Did they actually use some device there, or we could look at the fridge. You see, this is a typical power profile of a fridge. We could look at, oops, getting back here. Oh, now it's a different. We could look at washing machine. Nothing was there. So, as we have seen, for all the devices, we can just provide the information on how much they have been used in the past. It means we are measuring the usage of every device, which is quite some measurement demand there. Then we have here, what you see here is the power profile of the house in yellow. You see the prices that were there, and like between 10 and 40 cents per kilowatt hour. Just 3 different levels in the moment. And here you see the information for the next 24 hours. And you see the load limit, the power limit is just stable. Could also be like it's currently at 2000 watt, so like 2 kilowatt. Could be variable. We don't make it variable in the moment. You see the current price, 40 cents per kilowatt hour. So that's the information we provide on this area. Then we have a layout of the house. And there we can also, like you see, also temperatures are indicated here. So we do have temperature sensors there. It is quite warm in the moment, 24 degrees. We can also, I don't know whether this is running in the moment, like I could say, okay, I would like to switch on the light there, and this has all been redesigned or had to be updated to a new version. It looks as if this is not working in the moment, but in principle we have this possibility to click on areas here and then switch on the light in that area. So I will close that down again. And then we have here the kitchen. I just click on the kitchen area, and we see the devices in the kitchen. And then, for example, the coffee machine, the stove, and so on. I could go on the dishwasher, and then you see this interface, and there you see here the degree of freedom. I can. Here in this case, it's 9 hours degree of freedom, period of 9 hours for actually doing the dishes. I can modify that, and then I get more information. Now I will close that down again, or I could briefly give you this also. Like for the vehicle, we have an interface where we specify now, or where we can specify the next departure time. We certainly can also see the current state of charge. There's no vehicle in front, so we don't see anything there. But we can specify the next departure time. We can specify the minimum range that we would like to have. Can just, oops, this does not work in the moment. So some features are not running, but we could, in principle, modify the range that we have here to have some minimum range guaranteed. Okay, I would like to go then to the back to the presentation. So this is this way of presenting what's happening in the house, providing this information, and then, as I just said here, we have this interface for the kitchen elements. So there is a tumble dryer, kitchen, and so on. Here, for example, the tumble dryer. And there what you see again is the degree of freedom that we can adjust. And then here it says automatic start at 6 p.m. Now, this information is displayed as a response to there is a request for running that machine. And now the system knows what the profile for that period of time will be. External prices, typical load profile for that time period, and what is the best possible time for running that tumble dryer. And this is communicated to the user using that area there. And then the user can say, okay, I would like, regardless what this current situation is, I would like to run the machine right now. And then you can just switch on this start button and it will start. And it was interesting to see that, like, initially we didn't have that start button on the menu, and the first residents in the house complained that they could not control directly how the machine was running. And we said, okay, we put in that button, and they were highly satisfied to have that, and they never used it. Yeah, but it's just to provide this, and this is showing that it's very difficult to provide acceptable interfaces. Yeah, because sometimes you have to do something just to satisfy the people, even if you say, okay, I really don't want to offer that possibility, but they can do it if they want, and I hope that most of the time they won't use it. But it increases the acceptance significantly. Okay. I told you about the air conditioning, the phase change material, and I showed you this here already, this device showing the energy flows and also the electric vehicle, which, as you can see from that profile here, was actually having some time where it was recharging and then, no, it was discharging, and that's the time where it was being recharged. Okay, then the ingredients of the house is a lot of electronics, all kinds of controllers which are there, off-the-shelf devices which are integrated there with many cables. You will see that when you are visiting that. And this, like I said, we designed that. Now my chair is a chair of informatics. We are not the people who build smart homes and build electricity systems or controller systems. So we cooperated intensively here with people from electrical engineering. Although the principal design came from the people from my chair, actually. And now we have all the information from our systems, from the measurements, from the users. They have put in their preferences. So we have information on how all these nice devices are or can be used, our washing machines, the fridge, and so on. We get information from the user. We have information from the internet. And then we would like to use that in a reasonable way in the energy management system. And for that, we need some information. We don't need every information. So we have a hardware abstraction layer, HAL. Maybe somebody of you know or has seen the name HAL in some other connection. Two of you has read a book where HAL was important. None of you, illiterate people. Yeah. So this was in the book where HAL was a very friendly or very strange computer if you shift the letters slightly, you see that this is a resemblance of some large company. Yeah, so this is shift the letters by one letter, and you see what behind that abbreviation. But this was not was not behind our abbreviation of the hardware abstraction layer. It had nothing to do with IBM. So what did we do here? You need some kind of abstraction. You have all kinds of devices. And then we would wanted to be able to observe what's happening in that device and to control, to respond in some way, maybe do something with that machine. And the information that was observed there should be put to some observer in the house. So we would like to collect all the information about all the devices that we have in the house, and then maybe predict what will happen during the next day or during the next time period, make some load prediction, look at the current state, have some memory or some storage of the history data. And this will lead to some optimization. So here is some optimization element, some controller, which based on the optimization will send back information to the devices, as you have seen there on this menu, automatic start at 6 p.m. So these boxes here have certain tasks. This one here should observe and control that device. This here should observe and the house and predict what's happening there, provide information for the controller to learn, control, and optimize what's happening there. And then we have to communicate with the resident in the house and also with the external entities. So this is what our energy management system should be designed, or how it should be designed. And you always see this observe and control, and this is something we have actually taken over from an area which is called organic computing. And there we have designed an architecture for controlling systems which are more or less self-organizing. And in this book that is shown here, you find lots of information on organic computing system, the way they are designed, the way they can be used, all kinds of results from our research program that we have run here. So this was the background for designing this energy management system, and it's actually called Organic Smart Home because of this resemblance with the architecture, the system architecture for organic computing systems. You know that I'm teaching also a course on organic computing where we go deeper into the details of that. So before I continue with this energy-related stuff, I would like to briefly show you something about what actually organic computing is about, because there are quite a few students who are not taking my course on organic computing, and I would briefly tell what this background actually is about. So organic computing was started by workshops of the computer engineering community in Germany. Like, we are also supposed to have some research-driven teaching. And so you see here how research sometimes works, that all those who are active in research come together and try to find out in brainstorming sessions what are actually the challenges for the future. What do we have to work on? And we did that and found out several statements that information technology is more and more ubiquitously networked. And for that, we need new concepts for organizing all the information processing to prevent a situation like this where humans would be caught in a network of all these devices. So it has to remain manageable and controllable. And we made a few statements that future computer systems have to be designed with respect to human needs, whatever that means. They must be robust, adaptive, and flexible. So robust means if there are some disturbances or some faults, they should still operate reliably. They should adapt to different situations. They should be flexible in the way they provide functionality. And they should do most of these things by themselves in a self-organized way, but not against our desires, but they should be trustworthy, doing what we expect them to do. So these are the buzzwords that we had stated there. Certainly we had come up with a large paper on what kind of technologies we would need there. And if we combine all these aspects there, we said this looks like, in some way, lifelike behavior. The behavior is very organic, and so we call them organic computing systems. So this is what we would like to have. And this actually was something which was not completely our invention. It was not independent of other initiatives on ubiquitous computing, pervasive computing, autonomous computing, or autonomic computing, and many different initiatives had been active at the same time. 2002, 2003, 13 years ago. And so we said that organic computing, that it is not the question whether these adaptive and self-organizing systems will emerge, but how they will be designed and controlled. And this shows that there's a real challenge, that there will be systems. We know there are all kinds of systems which have in some way some self-organized behavior. They can communicate, and we have to make sure that the system architecture is adequate for that. That's the challenge we had seen there, and so we had to find out all kinds of concepts which could control these organic computing systems in a reasonable way. So many different topics were addressed and many research projects and many seminars that we had run at different places. And we were lucky that we, as said, many workshops and projects, they came up in a research program that was funded by the DFG, the German Research Foundation, from 2005 to 2011. I was actually the one who coordinated that, and we had 18 projects all over Germany with 2 million budget per year. And the idea was to design principles for these systems about like self-organizing systems, having some kind of emergent properties, and be inspired by things that we can see in nature, because there we can observe many self-organizing systems. We intended to come up with a toolbox how to design actually self-organizing systems. One of the tools was this template for an architecture for self-organizing systems, which we now have taken as the basis for our organic smart home. And we emphasized that we always wanted to have in mind technical applications, not just some toy application, but real applications where you need this behavior, and then come up with adequate system architectures for that. So we had many concepts or many projects for that. I don't show you all the individual projects, but just show you one of the essential things. What kind of system architecture do you need? And there is, like in the initiative for autonomic computing, there was an architecture designed which is called the MAPE architecture or the MAPE-K architecture. That's a cycle of operations. So you have a productive system and you monitor it, you analyze it, if you have an event that you have to respond to, you plan some action and you execute your action on that system. And so for that you need sensors to be able to monitor, you need actuators to actually do something on the system, and in this way, like this was the MAPE cycle of IBM, and it was applied mainly to data centers. So IBM almost completely focused on information processing in large data centers and enterprise server systems, because their intention was to relieve the people, the operators, from standard tasks, which could easily be automated and taken over by the system to be carried out in a self-organized way. They did not really look at other technical applications. We did that in organic computing. So there we have a system under observation and control. for example, the energy system or a traffic light or whatever you would like to look at, set of interacting elements. And this can operate on its own, but it will improve or it can improve its performance by having that observer and controller. So we observe what's happening, make some analysis in there. We have a controller which on demand will, or if necessary, will do something, which will perform some activity. And different from the MAPE architecture, we also always consider the user or some next entity which will observe also what's happening there, but which will provide goals and which will also look at the current system status. And so it is driven by external goals, and usually it is a multi-level organization. Now we have designed this in the following way. This is the observer having certain standard components. So we say this is a generic architecture. It means, what does generic mean? There will be many different situations, and you will instantiate your architecture in different ways. But in principle, you will be in need, or you might be in need of the following components, which are components for monitoring the state of your system, looking at system data, individual data, like data of the individual elements here. Maybe they can communicate in some way. You have to look at the interconnection structure, all kinds of things. Then you have to store what has been monitored, and you need a preprocessor, for example, to repair certain outliers or do some cleanings, some cleaning operations, filter out certain data, and then you analyze what's going on in the system. And from this analysis, you get some characteristic data, and this data will characterize the current situation. You might have a predictor, so this is something which is very important in some situations, that you predict what will happen in the future, and then you can combine that with the currently observed situation. And then, so this is the task of those devices, and then you come to the controller, which actually gets the characterization of the current situation. Here at the corner you have this model of observation, so we want to also be able to look at or to modify the way we observe the system under observational control depending on our objectives that we have. So you will not always observe the system in the same way, maybe modify the sampling frequency or look at different parameters, things like that. And now it's 3:30. I think I make a short break of 15 minutes, and then we start again after that break. Thank you.